Okay, so we're just going to do a continuation here. We've got a 1 cubic meter balloon filled with an unknown gas, has an apparent weight. It appears to weigh this in air at STP. Calculate the buoyant force, the actual weight, F sub g, and the density of the gas and the net force. Okay, so there's a lot there. All right, so the very first thing I'm going to do is find the F sub b. Now, this is a cubic meter balloon. And so we're going to take the cubic meter, and again, the buoyant force has everything to do with the fluid that it's in, and it's in air. That's its fluid. So the buoyant force is going to be 1.29 kilograms times 9.8. The buoyant force is going to be 12.7 newtons. Okay, now the apparent force is 1.37, and so what it really weighs then is we're going to do F sub A is equal to F sub G minus F sub B, and doing that formula you're going to find that F sub G must be 14.1 newtons. So basically that plus that. Okay, so F sub G is 14. That's what it really weighs. If we were to do the net force, the net force is going to be buoyant minus the F sub g of 14.1, and we're going to get a net force of negative 1.4 newtons. So this is sinking. This is definitely a sinking balloon. So the density of the gas must be greater than 1.29. So how could we find that? All right, we can do some other calculations here. In fact, we can go back to that formula we had before where we could use something that was completely surrounded by the fluid, and we could do that. So we have the F sub g that we calculated at 14.1. The F sub b was 12.7, I think. And the density of the object over air, the density of the fluid is air, 1.29. We find that the density of the object is 1.43 kilograms per cubic meter. And so obviously this is more than 1.29. So again, that's confirmation that this thing is sinking. So kind of going back to this whole idea of buoyant force again, we have a teddy bear in a glass bowl, don't ask why, and this is the water level. It's just floating level with the water. We'll go ahead and say that the teddy bear is like in a bowl that is like a sphere, so we'll do half of a sphere. Okay, I would probably tell you what to use for volume, but here's the volume. I'm going to go ahead and the radius would be 0.05 meters. Plug that in, and we would get the volume of this thing, and it would be that. Now, it's in fresh water, so again, unless it says it's seawater, we just assume it's fresh water, 1,000 kilograms per cubic meter, and we're going to get 0.262 kilograms. Now, the buoyant force, this is really what we're doing here, is finding the buoyant force. And if I multiply this by 9.8, that would be the buoyant force. And because it's floating, I could set that equal to F sub g. So this is also equal to F sub g. Again, I'd have to multiply this by 9.8 to get an actual newtons of force. But this is the mass. Now, because I can make this equality, what I basically can say is that this has to be the bowl plus the bear mass as well, right? Because it's floating. And so I subtract out the bowl, and the bear must weigh that. Okay, so you're going to be doing this in homework a lot, lots of different items, but that's basically it. So we're going to do a couple other questions here where we have a cross-sectional little boat. And we don't really care that it was floating before, but we're going to put some cargo on it, and that requires the boat to go down a little bit more. So we are looking at, because the cargo got added, an extra 2,903 cubic meters of water has to be displaced to continue to let it float. Again, focusing on the buoyant force and fresh water. If this were seawater, I would do 1,025. We're looking at 2.9 times 10 to the 6 kilograms for, again, this is buoyant force, but it's also F sub g. Okay, this also is all F sub g too. all F sub E, F sub G, because it's floating. So if I multiply this by 9.8, I get 2.85 times 10 to the 7th newtons. And this is buoyant force, but this is also what the cargo must weigh. This is the weight of the cargo. This is the mass of the cargo. This is the weight of the cargo. Because this is the buoyant force, it's floating. Therefore, that has to be equal. All right, last one. We have a ship. It's displacing 5 times 10 to the 6th kilograms of fresh water. Now this kind of goes to that homework problem where you have a boat in a sea of mercury, as weird as that is. Now, it has to displace this many kilograms of fresh water. But the question is not volume of water, which you could certainly do. Put 1,000 kilograms right here, 1 cubic meter here, kilograms cancel, and I've got cubic meters or volume of water. But the question is volume of mercury. But understand that it still has to displace kilograms of whatever fluid it's in. So mercury just happens to be extremely dense. So you aren't going to have to displace a whole lot to get it to float. That's how much mercury. Again, if this were fresh water, I'd put 1,000 here. If this were seawater, I'd put 1,025. It just depends. That's the volume that you need.